we had a pretty good day yesterday for our first day, but we're just getting started, right? We're just warming up yesterday. A lot of talk from the keynote yesterday in the halls and throughout the day. I thought that was pretty interesting. And it sounds like most of you thought it was interesting as well. So we're going to continue that tradition this morning. We have Wannes De Smet here. He's going to talk to us about his extensive analysis of the Calxeda server. I think we'll all find it interesting.
So, good morning, everyone. I'm Wannes from Sizing Servers, and I'm here to tell you all about our Sizing Service review of the Calxeda server. So, first up, some introduction. I work at Sizing Service, which is a small research lab founded in 2007 in Kortrijk, Belgium. Over the years, we've started offering some consultancy services towards companies to optimize their website. So we take their websites, we log it via realistic user patterns, and then basically we replay them a number of times to see how well it performs, as well to pinpoint eventual performance problems. But our main duty as a research lab is, of course, to do some research. So mainly we've been focusing on virtualization and power efficiency research. We've worked with lungs of Intel, AMD, and most lastly Calxeda. And then when we review a new piece of hardware, we put it up on a non-tech for everyone to see and read. So, but over the course of the last half year, we started hearing quite a bit of noise surrounding ARM servers. And then we got quite suspicious at Sizing Servers. Like, ARM servers, we're putting a smartphone CPU in a server. Could that actually work? So we Googled it a bit, found Calxeda, asked them quite nicely if they could send one over. Lo and behold, there it is. Now, you might notice it isn't quite different from a normal server. It has a normal 19-inch TU chassis, 24 drive bays at the front, nothing to write home about quite yet. But when you turn it around, things are starting to look quite different. So you have your drivers at the front, then the fans, and then quite a bit of interesting hardware. At the back, which you can't see that clearly on this picture, there's a large, mostly empty PCB with some slight sprinkling of components, but on it are also 12 pairs of PCI Express slots. And in these slots fit these energy cards, which I'll talk about a bit later. So at the back, you also have, for your outbound connectivity, 4 10 gig SFP ports, which is quite a lot, and a serial port to connect to your Node 0. So if you take a closer look to one of these energy cards, you can see lying on top of the server right there, and you take off the baffle, you get this little thing. So on this card, there are essentially 4 types of components that would be interesting to a server administrator. So you have your Calxeda SoC, hidden by a passive heatsink. Then you have 4 SATA connectors for each SoC, and then every SoC gets access as well to 1 mini DIMM slot in which you can fit a DDR3 memory. And of course, you see a pair of PCI connectors by which every energy card connects to the main board. So at this point, let's take a look at the core itself, or rather the SoC. So top right is your standard processor complex, ARM Cortex-A9, capable of running up speeds up to 1.4 gigahertz. Your standard ARM Cortex core, nothing special. Bottom left is your standard I/O controller. So as you've seen, SATA controller to power the SATA ports. PCI Express can be used in conjunction with other PCI Express cards, for instance, graphic cards or storage adapters. An Ethernet MAC, which can be convenient, and a secure digital external memory card controller. Now at this point, you have nothing more than your standard ARM SoC, one you can easily find in smartphones as well. What makes this Calxeda energy core stand out, though, is the energy core management engine, which basically is like a sort of BMC, like a remote controller, but then for the Calxeda energy core SoC. So what you're able to do is, everything you're used to do with a server remotely. You can power it on, you can reset it, you can read out basic sensor data, you can read how much power the core is using, and you can shell into a node via serial over LAN. So that is actually quite a critical component to make us think about this not as a normal ARM SoC, but rather more as a server, because there's an essential part to this, being simply as an infrastructure administrator to navigate and remote into your node. But Calxeda didn't stop there. They thought it would be rather nice, instead of having, for instance, take out an Ethernet port out of all of your SoCs, which can be up to 48 in this chassis, which could get quite a bit messy if you have 48 cables taken out of it. So they developed a fabric, not only for Ethernet traffic, but as they use ZAUI as a low-level protocol, they're able to route quite basically any number of protocol and data over their own fabric. And what this energy core fabric switch does on each SoC, is basically autonomously routes ZAUI packets along the fabric. So the processor core doesn't need to be on. This operates completely by itself and makes sure that every packet, if you will, reaches its destination. The fabric isn't limited to the chassis itself. It can span up to 4,096 nodes, which is, quite a lot. But considering this is all very nice, because they did good work there. But then, our sizing servers' interests are really to play out, because how well does it actually perform when compared to Intel cores? So first off, some intrinsic benchmarks. The first one measuring memory bandwidth. So its main competitors, we find at the top the Xeon E5-2650 low power processor running at 1.8 gigahertz. At the lower end, we find an older Atom released in 2008. We find the Atom N450 released in 2010. Then we find the Calxeda Energy Core. And then above it is the latest and greatest Atom from Intel available at that moment, which was released in the fourth quarter of 2011. And what you're able to see is, for memory-intensive applications, the Calxeda Energy Core isn't there quite yet. It still kind of outperforms the older Atom cores. And obviously, when comparing it to a Xeon E5 server, that's quite a large gap as well. But when we move on to another benchmark, results get a bit more interesting. So what we have here is a 7-zit LZMA compression and decompression benchmark. And what you can see is it can actually beat with, seeing as the lower two atoms have only 2 cores. 2 cores from the Calxeda server can actually beat the older atoms. And when you compare it to the most recent Atom, it's very close. Same goes for compression as for decompression. It can't beat it quite yet, but it is coming very close to beating the Atom as such. Now, something I imagine you guys will be doing a lot is compiling on the core. So what we have, again, is a very comparable result to the compression and decompression benchmark. If we consider pure core performance, one of the cores of the Calxeda Energy Core server isn't able to beat the Atoms just yet. But when combining all 4 cores, it is capable of beating the older atoms and, again, keeping up quite nicely with the latest one. So just to be sure here, the GCC used was the one available in Ubuntu. It was optimized by you guys, so we used the best one, we think. And we actually ran a 7-zip compilation as such, which produces these results. But at this point, we can't go to our customers in our research group and say, like, it can compress decently, it can compile well. They won't be as much interested in that. What they do like to know is some sort of real-world performance. And that's exactly where we come to play, because over the last 5 years, a developer at Science Service has been churning away and writing code at Vapors, which is our own virtualized application unique stress testing. A bit of a clunky name, but it is a great piece of software because it enables us basically to take real user patterns from websites or basic SQL logs and the likes, to add some parameters into it so we can make it a bit more random to make it even more realistic, have some delays programmed into the log, like for instance, a user won't click very fast, it will always have a second or 2 delay. And then it enables us to distribute these tests up to a certain number of servers, in which case, in this case, of course, we wanted to test every node in the system, which does results in 24 simultaneous stress tests. Now, if we were to compare 24 different nodes versus one node, the big Intel one with 2 Intel Xeon processors, it was going to be quite a bit of an apple versus oranges comparison. Just, that's the way it was going to be. So we try to make it a bit more, try to simulate the Calxeda box on the Intel server in a quite realistic scenario as well, by just creating 24 VMs atop of ESXi. So each node was running Ubuntu 12.10, Apache and PHP were the latest up-to-date versions. Here are some specs for you all to enjoy. So our Intel server was a Supermicro twin, one disconnected. It has 2 Intel E5-2650 low-power processors, along with 64 gigs of DDR3 memory. It also has a fat networking card, 2 times 10 gig SFP, connected, of course, to a 10 gigabit switch, and a 1280 watts 80 plus platinum power supply. Now, the Calxeda system, as you know by now, 24 Calxeda nodes, fitted with each node had access to 4 gigabytes of low power, low voltage 4 gigabyte memory, and the whole was powered by a 750 watts Supermicro power supply. Now at this point there was another issue we had to take care of, because the Calxeda, as it came shipped to us, the Boston Veridis server system, had an SSD in every drive bay, so every core, every node had access to its own SSD. Now, as we were using a twin, we can't jam 24 SSDs into 6 drive bays. That would have been a bit difficult. But instead, we could take this a bit further and eliminate as much differences between those systems as possible. So we choose to boot all the VMs and the Calxeda nodes to boot them from our SAN via Pixie, and all the disk images were placed on a RAID of Micron P300 SSDs via a Leo iSCSI target. So there you go. Now onto some results. So as you can see for yourself, when in the low concurrencies, the Boston Veridis server isn't quite able to beat the Xeons quite yet. But when you take it up a bit, up to 35 concurrent users, and then of course 50 and 75 concurrent users, the Calxeda system is able to beat 24 Intel VMs. But that isn't the whole performance picture. Of course, you want your response times to be good as well. So what we have here is basically the same story. The Calxeda server performs a bit worse at lower concurrencies, has a higher response time, but once we go up to 35 concurrent users, you see that the response time is quite a bit lower than their Intel counterparts. Now, as you can see, in comparison to the latest charts, there has been an additional metric here. We have first had the Boston Viridis, and now we have Boston Viridis optimized. That is because we didn't have as much experience with ARM servers yet, so we kindly asked the guys from Calxeda to help us a bit in tuning and make it a bit more power efficient, which they kindly did. So, as you can see, the optimization did have a slight impact on response time, but they did have a great impact on the power usage, because basically, if you want to build a server that's more powerful than an Intel server, that's not that difficult. You just put however many CPUs in the system, and then it probably will run. It will have more power than an Intel box. What is difficult, however, to do is make it run more efficiently, using less power. And look, the Viridis using the Calxeda energy cores did it. When run idle, a standard out-of-the-box performance, it does use a bit more energy than power than the Xeon. But when the optimized versions, if you consider them, they use less power in every scenario. So they use less power when idle, use less power when they're running an average load, and they use less power at a peak load. So this is, quite a hooray moment for us at Sizing Servers, because we were able to see that at this point, Calxeda's server was actually able to keep up performance-wise and play out its ARM advantage, which is that of being energy efficient. So to give some more details on these metrics, those were actually measured at the wall, so we didn't use any of the internal measurements provided. We wanted to be sure we have our own precise equipment for measuring power. And yeah, the conclusion is simple. Calxeda at this point, in this scenario, is able to outperform our Intel server box. So that is actually a rather good note to end on for a conclusion. So what we can see for our Sizing Servers is, it is actually first and foremost to be at least a bit realistic to say to one of our customers, to advise them this, it has to be like a serious server. It can't just be like a number of smartphones in a box, for instance. So it has remote management. They have thought about networking quite well. They have made a good fabric which allows you to run over 10 gigabit speed, so that's quite a lot. The cores itself can't put that amount of traffic through. As you've just seen, power performance ratio is good as well. It is, in that scenario, it is better than the Xeon E5 processors system. And what I didn't mention is this is also quite a capable I/O machine. So it has 5 10 gigabit PHYs, which quite allow it to have a lot of I/O communication with components within the system. And that would actually be a very good fit for, let's say, storage solutions. So it seems Calxeda took note. They have been working to get a distributed storage system working on their servers called Ceph. Foxconn had their way with the energy cards as well. As you can see, that big box in the middle, There are 12 energy cards at the back with a total storage capacity of 24 terabytes. And then Aeon has built a storage appliance as well based on the energy core. So at this point, it will be interesting to know, looking forward, will our customers, be throwing their Intel boxes in the trash and saying, yeah, we're going all Calxeda, this looks nice? Probably not, sorry to say, but at least starting, which was more of a first adopter system from Calxeda, this is actually rather good news, as we are able to see that performance isn't terrible. More on the contrary, it is actually able to perform quite well. So that's a positive note to end on. Maybe I'll be here sometime in the future presenting our next review of the Calxeda Midway server, which will be based on the Cortex A15. So thank you very much for your attention. Can I answer some questions?
Anyone? Any questions?
Yeah, the benchmarks for the Xeon, are they 64-bit or 32-bit executables?
They were, I think we compiled them as 32-bit.
Anyone else?
Is that the way you would optimally configure the Xeon system?
No, ideally you would run, well, it depends on the environment first and foremost. If this is a share hosting environment, it's quite logical to have 24 VMs on the system for each customer his own VM. So in that respect, yes. But if you want to get the most performance out of the Xeon system, you would probably ditch the hypervisor and run Linux on the system itself. Now, I have tried to give some performance details when doing exactly that, but due to some strange MySQL locking issues, it just performance collapsed and it wasn't a bit better, so it wasn't. I wasn't able to put it into the slides today.
What was the virtualization system?
We used VMware ESXi.
Over in the corner?
I've thought that putting up a system that slightly outperforms the Intel and measuring the power and comparing the results.
So I think you mean this slide then, or?
Yeah, but some configuration that would actually outperform Intel in each, from each point of view, each test you do. Because, you showed us a lot of graphs where the performance was lower than on Xeon.
Yeah, performance from the Xeons. So I think you mean power statistics for the top 3 tests.
No,
The earlier slides where you were not showing the real world.
Oh yeah, we haven't, because we were only running those tests on one core, so yeah, they weren't quite usable power data from that one. To do such a thing, we could in fact run it on each core, but we haven't done so, sorry, there are no power details for those first tests.
Have you run the same benchmarks using different hypervisors on the Intel platform to see ESX, KVM, or Zen have any impact?
We haven't done that because, well, first and foremost, we mainly work with ESXi, and it was more of a focus on the Calxeda system to get the most out of that than out of the Intel system. So at the Intel system, we just went with what we knew and what worked. So yeah, we haven't tested on other hypervisors on the Intel box.
At the end, you said kind of
Well, based on our performance, based on our testing, I can say that it is able to put out like more than a gigabit of networking traffic, but that's like a ballpark number. Other than that, storage performance is something we didn't test as we went over quite soon to the boot from iSCSI.
Okay, thanks very much.
Thank you.